In this first video for section 14.6, I would like to introduce the concept of directional derivatives and show you how to compute these things. Now at this point in the class, the only kind of derivatives we know how to take of multivariable functions are partial derivatives, which tell you how a function f changes if you move parallel to either the x or the y axis. To be precise, our partial derivatives were given by these two limit formulas here. To define both of them, we set up difference quotients, where our numerator corresponds to some change in output, and our denominator corresponds to some change in input. In the partial derivative with respect to x, we allow only our x coordinate to change, moving between x0 plus h and x0, while we fix our y coordinate at y0. While for the partial with respect to y, we fix our x coordinate at x0, but allow our y coordinate to vary between y0 plus h and y0. There is an equivalent way to think about these partial derivatives. To describe this, let me begin by parameterizing the lines in the plane passing through x0, y0, which are parallel to the coordinate axes. For the x-axis, I can take the vector function r1 of t, which will look like x0 plus t, comma y0, which I can also write as the position vector for our point, x0, y0, plus t times I, where I is the unit vector in the direction of the positive x-axis. For the y-axis, we can have something like r2 of t equal to x0, y0 plus t, which looks like the position vector for our point, x0, y0, plus tj, where j is the unit vector pointing in the direction of the positive y-axis. Now, the composition, f of r1 of t, is a single variable function, whose values are the values of f along the line parallel to the x-axis passing through the point x0, y0. If I take the derivative with respect to t of this single variable function, then I get the rate of change of f along this line. And if I plug in at t equals 0, then I will get the rate of change of f at the point x0, y0 in the x direction. In other words, I'll get the partial derivative of f with respect to x at the point x0, y0. The same logic works for y, and the partial with respect to y will be the derivative with respect to t of this f of r2 of t, evaluated at t equals 0. Something to notice here is that the only difference between these two formulas is that one uses I and the other uses j. When I'm taking the partial derivative with respect to x, I use I because it points in the direction of the positive x-axis, while when I'm taking the derivative with respect to y, I use j because it points in the direction of the positive y-axis. Now I and j are special unit vectors because they point in our coordinate directions, but there are lots of other unit vectors out there. So one should naturally ask, can I compute the rate of change of f in other directions, other than just I and j? This is exactly what the directional derivative seeks to compute. It takes as its input a function f, a point, x0, y0, and a unit vector, u equal ab, and it outputs a number, d sub u, f of x0, y0, which represents the rate of change starting at x0, y0 of f in the direction u. Here your book has given the limit definition of the directional derivative. If you'd like the alternate interpretation, then you can think of the following. The vector function x0, y0 plus tu is a vector function which parameterizes the line through x0, y0 in the direction u. If you compose f and r, you get a function whose values are the value of f along this line. You can then differentiate this function to get the rate of change of f along this line, and then plugging in at t equals 0 gives you the rate of change at the point x0, y0. And so the only difference between a directional derivative and a partial derivative is that we take a general vector u instead of the coordinate vectors I or j. I should note that while the formula defining the directional derivative makes sense for any sort of vector, when you're computing directional derivatives, you only want to use unit vectors. Some books might have different conventions and allow you to take directional derivatives of non-unit vectors, but as far as our text and this course is concerned, a directional derivative always takes as its direction vector a unit vector. Let me try to be a little more concrete. Here I've given you the contour plot of a function f of xy equals x squared plus xy minus y squared. I've centered everything at the point 2, 2, and so that will be my x naught, y naught. I've also drawn 3 vectors and 3 lines. You have the unit vectors I and j, and we have this diagonal unit vector u, which has components root 2 over 2 and root 2 over 2. The lines in the directions of these vectors passing through the point 2, 2 are parameterized by these vector functions r1, r2, and r that I defined earlier. What the directional derivative in the direction of u of f at the point 2, 2 is meant to represent is approximately the change in output divided by the change in input. What I mean exactly is the following. Our output ends up at f of 2 plus root 2 over 2, 2 plus root 2 over 2, and it started at f of 2, 2. So if I take the difference, this is my change in output. As for my change in input, I traveled 1 unit in the u direction. So I'll think of my change in input as 1. If you plug this into a calculator and evaluate, you'll get approximately 3.3. A little bit later, we'll compute this directional derivative exactly. And so keep this number in mind and we'll compare how close we got. So how do we compute the directional derivative in practice? Well, what this theorem tells us is if f is a differentiable function, then we can compute the directional derivative in the direction u equals ab using this formula. It's important to note that this formula just involves the partial derivative with respect to x, the partial derivative with respect to y, and the components of the unit vector u. And so therefore, if we'd like to ever compute the directional derivative, all we'll need to do is compute our partial derivatives and put them together with the components of our unit vector according to this formula. We'll prove this theorem in a moment, but first let's use it to find the exact value of the directional derivative that we approximated a few seconds ago. In that example, our function was the function x squared plus xy minus y squared. The point was the point 2, 2, and the unit vector was the vector root 2 over 2, root 2 over 2. According to the formula, I'll need to compute first our partial derivatives. So I'll compute the partial with respect to x and get 2x plus y. If I plug in at 2, 2, I'll get 2 times 2 plus 2, or 4 plus 2, which is 6. If I compute the partial with respect to y, I'll get x minus 2y. Plugging in at 2, 2, I'll get 2 minus 2 times 2, which is 2 minus 4, which is negative 2. And therefore, the formula says that if I want the directional derivative in the direction u of f at 2, 2, I take my partial with respect to x, which was 6, multiply it with the x component of my unit vector, which is root 2 over 2, and I add that to the product of my partial derivative with respect to y, which was negative 2, times the y component of my unit vector, which was root 2 over 2. If we simplify things here, we'll get 3 root 2 minus root 2, or 2 root 2. And plugging this into a calculator, we have approximately 2.8. You can compare this to the value we calculated a little earlier, which was 3.3. That's pretty close, so I'm reasonably sure that we did our calculations correctly. All right, it's proof time. How are we going to prove this theorem? Well, first off, remember the definition of the directional derivative. We have that the directional derivative in the direction u of f at a point x naught, y naught is the derivative with respect to t of the composition f of r of t evaluated at t equals 0, where this vector function r parameterized the line passing through x naught, y naught in the direction u. And so it looks like x naught, y naught plus tu, or alternatively x naught plus ta, y naught plus tb. Now if I want to take the derivative of a composition, then we have to use the chain rule. So if we apply the chain rule, then the derivative of f, thinking of it as a function of t, will be the partial of f with respect to x times the derivative of x with respect to t plus the partial of f with respect to y times the derivative of y with respect to t. Now here, del f del x is just f sub x, but the derivative of x with respect to t, I need to compute by looking at this x naught plus ta and differentiating with respect to t. I'll get an a. On the other hand, del f del y is f sub y, and to figure out what dy dt is, I need to look at this y naught plus tb and differentiate with respect to t to get b. And so, if I want the directional derivative in the direction u of f at x naught y naught, all I'll need to do is plug in at t equals 0. When t equals 0, x equals x naught and y equals y naught, so I'll get f sub x of x naught y naught times a plus f sub y of x naught y naught times b, which is exactly the formula that we were looking to establish.